Hi, this is Shannon Seaver. Today we're looking at irrational numbers. This is part one of a two-part video. On our agenda for today is to define irrational numbers and to simplify square roots. We're going to perform some operations with square roots, but then we're going to save part of that for the next video, as well as to rationalize the denominator will be on the next video. So the first thing I want to talk about is what is an irrational number. A rational number is the set of numbers whose decimal representations are neither terminating nor repeating. Remember, when I say terminating, it's like a decimal that says 0.25 and there's no other numbers past it. That's a terminating decimal. And repeating is a decimal that's like 0.535353 repeating. It's neither of those types of decimals. What I mean by irrational number is often I tell students that it's a messy decimal. It is kind of random and it goes on forever and ever. An example of that would be pi. If you were to put pi into your calculator, it starts off as 3.14 and then it goes on forever and it doesn't have a pattern to it whatsoever. The same thing as square root of 2. One of these numbers that we're going to look at that are rational are radicals. There are some radicals that are not irrational. However, let's just talk about what a radical is. First of all, this is the parts of a radical. We have the radical sign, which is like the square root sign itself. And notice this has a 3 here. That means the cubed root or the third root. Normally, if it doesn't have that, if it's just blank, that you can assume is a 2. So a square root, the index on that would be a 2, but normally it's not even there, so you can assume that. The vinculum line is the top part of the line, and then everything inside the radical is the radicand. So those are some vocabulary words that you probably should write down in your notes. Before we get any further, we're just going to look at the square root, the second root of radicands, and I want to talk about what a perfect square is. So when I talk about a perfect square, it is a number in which you have something squared. So like 0 times 0, which is 0 squared, is 0. So the numbers that are in bold here, they're all what I would call perfect squares. And they are the numbers of 1 through 15 squared. These are some numbers that you really should know. It will make simplifying square roots a lot easier for you in the future. So you need to write these down and try to put them to memory. And if you don't have them in memory, just go backwards. Think about, well, what's 3 times 3? What's 4 times 4? Those are all perfect squares. The product rule is when you have a square root of one number times the square root of another number. So here, if you take these two and you multiply them, it's actually the same thing as saying the radical of the square root, the radical of a times b. So let's look at this as an example. We have 2 times 5. That is the same thing as saying 2 times 5 inside the radical, which happens to be square root of 10. On this particular one, a square root of a number that's itself will always end up being itself. So the answer to this is 7, and I'm going to show you why. The square root of 49, which is 7 times 7, is 7. So anytime you see a number times itself, it's going to be that number without the radical. And on this one, we can take 6 times 12. So that would be the square root of 6 times 12, which happens to be 72. Now, this number can be simplified, but we will talk about that in the next slide. Simplifying square roots. When we simplify square root, we want to take out any perfect square that is in there. So one of the ways that we do this is actually putting the numbers into their prime numbers. So I can take 75 and take the square, not take the square root, but find that 5 goes into 75 25 times. Nope, 15 times. Okay, and then 5 also goes into 15 3 times. So I can write this as the square root of 5 squared times 3. Notice that we have the number 5 squared here. Because it's to the second power, I can take it out of the radical. So this is the same thing as saying 5 square root of 3. Okay, so that's square root of 75 simplified. Let's do the same thing for 500. 5 times 100, 10 times 10, 2 times 5, 2 times 5. So I can write 500 as a square root of 2 times 2, so it'll be to the second, times 5 to the third. Well, 2 is to the second power, so I can already take that out. But I'm going to rewrite this a little bit more exact here. That'll make it a little easier to see. Notice I took 5 to the third and made it 5 to the second times 5. So now I can take anything to the second power out of the radical. So this will be 2 times 5 square root of 5. Well, what is 2 times 5? That's 10. So it'll be 10 square root of 5. And this is my simplified square root for 500. 17. Can we take the square root of 17? Well, if I were to take it and put it in its prime numbers, it's already in its prime numbers. 17 is a prime, so there's nothing I can do to simplify that one. I want you to take a moment right now and try to simplify this yourself. Stop the video and come back and check your work. All right, so for the first one, I got 2 square root of 3. And on the second one, I had 2 square root of 15. And the third one, I couldn't reduce. It's primed, so it's already square root of 55. So we just did the product rule. We also need to talk about the quotient rule. So if you take the square root of 2 numbers and you're dividing, you can actually put the radical around both of them. So it would be a over b, like this. So I could say this one is really the radical of 75 over 3. And I can reduce that, because 75 divided by 3 is 25. And I know that 25 is 5 squared. So the answer to this is just 5. Now, on this one, I think this one was supposed to be a 3. I'm not sure. But if it isn't, let's just leave it the way it is. I'm going to say the square root of 45 divided by 2. Now, I can't really reduce that because 2 does not go into 45, so we would leave it just like this. Say, for instance, it was 3, though. We'll take the square root of 45 divided by 3. That would be the same thing as saying the square root of 15. And since 15 is 5 times 3, there's nothing doubled in that. It's going to be this by itself. Now, I want you to take a moment and try it yourself and come back and check your work. So on the first one, if you took it down to its prime numbers, you would have 2 to the 4th, and 2 squared times 2 squared is 4. Or you could remember that the square root, 16 is a perfect square, and because of that, 4 is the outcome of that. On the second one, the answer to this is 2 square root of 2. Now, there's something special in math called the golden ratio. This is a square that is found in everywhere, in nature and everything. Our human shape is the golden ratio. Much art is the golden ratio. So if you notice that you have one side of the rectangle is 2, and the other side of the rectangle is square root of 5 plus 1. I challenge you to go on the internet and go to Google and put in the name golden ratio and see what images that you get coming up for that. That is the end of this lesson.